Hi, in this chapter we are going to talk about the coloring problem, so let's get started. It is a typical NP-complete problem. The core of the problem is pretty straightforward. Just color the vertices of a graph such that no two adjacent vertices share the same color. This is called the vertex coloring. Besides vertex coloring, there are other kinds of coloring such as the edge coloring or the face coloring. But the vertex coloring is the one that has many applications. So we are going to focus on this type of coloring. Reach popularity with the general public in the form of the popular number puzzle Sudoku. The smallest number of colors needed to color a graph G is called its chromatic number. And there may be more than one solution. So for example, we can color a graph with 4 vertices in 12 ways with 3 colors. So it may be redundant, yeah. It has several applications. For example, bipartite graphs. Determining if a graph can be colored with 2 colors is equivalent to determining whether or not the graph is bipartite, and thus computable in linear time using breadth-first search. What is a bipartite graph? A graph whose vertices can be divided into 2 disjoint sets, U and V. U and V are independent, of course, such that every edge connects a vertex in U to one in V. And we have discussed problems in the maximum flow minimum cut theorem, and we saw that there are a lot of applications concerning bipartite graphs. So this is a certain application of the coloring problem. Another application is making schedules. For example, we want to make an exam schedule for university, and we have different subjects and different students enrolled on every subject. Many subjects would have common students. And how do we schedule the exams so that no 2 exams with a common student are scheduled at the same time? How many minimum time slots are needed to schedule all exams? These are the questions that can be easily answered with the help of a coloring problem, and this is why it's very important to be familiar with these kind of algorithms. We are going to see that there are 2 main algorithms, the greedy one and one that relies on some heuristics. It is called the Welsh Power algorithm, and this is why it's very important to be familiar with these kinds of techniques, because there's lots of applications of the coloring problem. So this problem can be represented as a graph where every vertex is a subject and an edge between 2 vertices means there is a common student. So this is a graph coloring problem where minimum number of time slots is equal to the chromatic number of the graph. Another very interesting problem is the radio frequency assignment. When frequencies are assigned to towers, for example, during mobile communications, frequencies assigned to all towers at the same location must be different because of the interference. And how to assign frequencies with this constraint? What is the minimum number of frequencies needed? It can be very important as far as engineering concepts are concerned. So it's a very important application too. This problem is also an instance of graph coloring problem where every tower represents a vertex and an edge between 2 towers represents that they are in range of each other. And of course, as far as operating systems and softwares are concerned, maybe this is the most important application, the register allocation problem. In compiler optimization, register allocation is the process of assigning a large number of target program variables onto a small number of CPU registers, and these problems can be solved typically with the help of coloring algorithms. And of course the map coloring. This is the typical coloring problem, by the way. We want to construct a map of countries or states where adjacent countries or states cannot be assigned the same color. And several mathematicians came to the conclusion that 4 colors are sufficient to color any map. This is the so-called 4-color theorem. So, as I said earlier, there are 2 main approaches, the greedy solution and the Welsh-Power algorithm. Let me tell a few words about the greedy one. Because the problem is an NP-complete problem, so we just want to get an approximate solution. And it doesn't guarantee to use minimum colors, but it guarantees an upper bound on number of colors. So the basic algorithm never uses more than d+1 colors, where d is the maximum degree of the vertices in the given graph, or the branching factor. I'm going to talk about this later during the illustration. So, for example, we have a graph. We have 5 nodes, 1, 2, 3, 4, and 5. And it's very important that this graph is undirected. And we just have to set some preferences. I mean that, for example, we traverse the nodes in numerical order. 1, and then 2, and then 3, then 4, then 5. And the main approach is that, because this is the first node, we assign a certain color. In this example it is blue, but it can be red, green, whatever you prefer. And we keep visiting its neighbors. In this case it is the 2 and the 4. I mean, we keep hopping to the 2 because this is the next one in the numerical order. And we see that we have to color it a different color. For example, red in this case, because we have a neighbor that has a color blue already. So we cannot use the color blue, because in that case there would be 2 nodes, 2 adjacent nodes that has the same color, and it is forbidden in the coloring problem. Then we hop to the next node in the numerical order, which is the node 3. And we can see that we can reuse the color blue, because 2 has a neighbor 1, 4, and 3. And if we use the color blue, that means that we are not violating the coloring problem basic concepts and no 2 adjacent nodes with the same color. As far as node 4 is concerned, we cannot use blue, because the neighbor of node 4, for example, is node 1 or node 3 that has color blue. So we cannot use this color. We cannot use red neither, because it is the neighbor of this 4 node. So we have to use a different color, for example, yellow in this situation. And then we hop to the next one. And we can color this node blue, because we see that the only neighbor of or node 5 is node 4 that has a color yellow. So we can reuse our first color, blue. And it's very important when we check whether we can reuse our colors, we have to start from the beginning. So we have to track that the first color we used was blue, then red, then yellow. And when we keep hopping from nodes to nodes, and on each iteration we have to decide whether we can use the first color. And we came to the conclusion that in this case, yeah, we can use the first color. But if not, then we have to decide whether we can use the second color, then the third color, then the fourth color. And it is an optimal way. This greedy solution is usually very, very good. Yes. Another approach, as I said earlier, is the Welsh-Powell algorithm. It performs better usually than the greedy solution, because we use a simple heuristic. We should eliminate the nodes with highest valence as soon as possible, because the more neighbor a node has, the more problematic it gets to color that given node. And it's very important that the valence means the number of neighbors. I don't know why they gave this name, but whatever. So the algorithm is that find the degree distribution or the valence for the nodes. We just have to calculate for each node that how many neighbors does that given node have, and sort in descending numerical order by valence. Color the first vertex with highest valence with color 1. Iterate through the list, color every vertex not connected to the colored vertices with the same color. In this situation, it is the color 1, but as we keep incrementing our color number, it can be 2, 3, whatever. Cross out all colored vertices from the list, and repeat until there are no uncolored vertices left. So it's very, very easy. Let me illustrate how it works. We have 1, 2, 3, 4, 5, 6 nodes, A, B, C, D, E, and F, and we have to calculate the frequencies. It's not the right name. I mean, it's not frequency. It is the degree distribution or the valence. As I said earlier, we have to calculate that, for example, A has 2 neighbors, B and C. B has 2 neighbors, A and C. C has 4 neighbors, A, B, D, and E. E has 3 neighbors, C, D, and F. F has just only 1 neighbor, the E. We just have to calculate it. Then the next step, as I said earlier, we have to sort according to the frequencies. It can be done in ordo n log n time complexity, where n denotes the number of vertices, with the help of quicksort or merge sort or whatever. So it's kind of a quick procedure. And we came to the conclusion that we have to start our algorithm with node C, because it has the most neighbors. It has neighbor A, B, D, and D. So we start the algorithm with this. We set the color to blue, for example, and we cross over. I mean, it is no longer in the list, so I denoted it with color red in our table. And we keep iterating through the list and check whether are there any nodes we can set the color blue. And we came to the conclusion that A, we cannot give the color blue because it's a neighbor of C. B is the neighbor of C too. D, E, they are not allowed to color blue. But F, we can color F blue because it's far away from node C. It's not the neighbor of C. And in the next step, we have to we continue our algorithm with the next most frequent node, and it is the E. So we give the color, for example, red. And we keep iterating through the list again and check whether we can reuse this red color. And we came to the conclusion that we can reuse this color if there is no neighbors of the given node. So for example, we can use the red color for node A because we see that A is not a neighbor of E. And that's all. We cannot color B or D to this red because it would violate the coloring problem main concepts. So we keep going, and B is the most frequent element in our updated list. So we give the color yellow, and we iterating through the rest of the list in order to check whether we can reuse this color. And we came to the conclusion that yes, we can reuse this yellow color for the node D. And that's all. We ended our algorithm. So as you see that this is a bit smarter algorithm. I mean, we have a heuristic. The main concept is we have to eliminate step by step the nodes that has the highest valence. I mean, that has the most neighbors. And then we keep iterating until all the nodes are colored. So, thanks for joining me. Thanks for watching.